Hello, it's me again at the shop here. I'm at the bigger shop with the bigger pieces of equipment, but the machine work in this video is going to be done in my garage on the little Haas mill. What we're going to be doing is comparing the Esprit software to the Fusion software on the thread milling cycles and see how they differ. As well as I'm going to show some images of some thread mills that we've used here in the past. So let's get right to it and look at the thread mills, and then we'll see the software and the machining. Are the ones we're going to be actually using to mill with in this video. And this type of tool is really good for if you have a long overhang, you got to make kind of a long thread in a hole, and it works really good for that. And this is a half 13 thread that we're doing in this video, and this is the same tool with a full cut length. It's basically the same exact tool I've used. Well, this is a newer one. I've used ones like this. I modified this tool because I had to make a thread longer than the cut length of the tool, so I ground some clearance. And you'll see in the video how you handle this in the software for that. So this is for a 1'8" thread. Here's another style of tool it's kind of a skip tooth design. So you have to make a couple of revolutions to actually get the thread in it, but you don't have to go all the way out the hole. You just make a couple of 2 or 3 revolutions, and then you've got the thread. And this is just a general V type of threading tool. This is the diameter 135, 60-degree thread. This is actually sized to do a 1032 thread here. There's a pipe threading tool. This is sized to do a 1/2 and a 3/4 inch NPT pipe thread. It's got a 14 pitch lead on it. These are just some threading tools we had around the shop here that I've used in the past. Here's an inserted thread mill. I believe this is a Vardex brand. To do that kind of a thing. Here's a much bigger version of that little thread mill. It's got only the single point on it. This one worked very nicely. This tool that we're going to use in the video also has through the tool coolant. Whenever I can, I use tools like this on the bigger machines with high pressure coolant, because this really dramatically increases the life of the tool to do that. Here's a ISCAR. This is a 40 pitch 440 thread. If I can get a better focus on this. So this is more or less the same as the first tool I showed, it's just a smaller one. So these are some different threading tools. I just went around the shop and collected some. Thought I'd show them so you can get an idea of the different styles of tools to thread with. Well, this is one here that I had to do a very large ID thread, and it mounts on a shell mill mount. I believe this is also an 8-pitch thread. If you remember in the last video, I milled a thread with even a lathe threading bar like this. But you have to pay attention with this because the insert has to swing big enough in diameter so that the back of the bar clears. Some threading bars, the insert's set back on there, and they won't work for milling a thread, but this style of bar will. You also have to probably grind this. This isn't the bar I used, but you have to grind that insert screw as well so it wouldn't rub. Here's our model in Esprit of what we're intending to do on the machine, and we're kind of comparing the Esprit threading cycle to the Fusion threading cycle. So all of this up here is just preparing the stock to cut these 2 threads. So I'm not going to talk about that at all really in this video. What we're going to concentrate on is the threading cycles in this case. So the threading cycle on any CAM software has a lot to do with the tool definition. So let's look at the tool definition of this tool for this thread. And we're going to look at the actual tool. This is the shank and everything, but what we're interested in is the tool itself. So the tool's diameter is 350 thousandths. It's got a 60-degree angle to the thread. This might be different depending on the thread style you're making, but this is the important one, the pitch of the thread. So this is going to be a half 13 thread, so 1 inch divided by 13 is 0.07693 inches. And there's no taper to the thread. If this was a pipe thread, you'd be entering an angle here. This is critical though, the cut length of the tool, because this tells the software how many passes in the upward and downward or the Z direction it has to take to generate the thread's length. And so this tool has 3 points, as you saw earlier in the video of the different style of tools. And so this number is the pitch times 3 is what it is. It's got 3 flutes. It's 260 thousandths above the tool's cutting edges, so we don't rub the shank, and it's sticking out 1.5 inches from the tool holder. So these 2 entries are the most important, the pitch and the cut length, and the angle would be if this was a tapered thread, but it's not a tapered thread. So that's the tool's definition, and you can see in this case why it's important, because the thread's depth is 900 thousandths deep, but that tool obviously can't make 900 thousandths, so it has to take 4 passes in the Z direction. So I like the way Esprit specifies their threading cycle a little better than Fusion, because you're actually giving it the dimensions of the thread here. You're telling it it's a 1/2 inch in diameter and the major diameter, because this is an internal thread, and the hole here is 422 thousandths, the tap drill for half 13, and the thread is 900 thousandths deep from the top of the feature, which is in this case the top of the part, down in depth. That's not the depth of the hole, that's the depth of the thread in the hole. And we're climb milling the thread. You could conventional or you can climb mill it, and we're going in the downward direction in this case, because this tool can't make the full length of thread because the cut length's too short. It'll start the upper passes first and go downward. You can either go down or you can go up. I prefer to go down when I make the thread for a reason I'll explain in a minute here. The start angle is, this is the rotational start angle of the thread. If that was important, you'd have to put in an entry there, and it's generating the thread with arcs in this case, because a straight thread it can just use helical arcs to generate it. You can also generate a tapered pipe thread with arcs in this software, and that works alright. I've done that before. Some machines might not like it, and you might have to use segments for that kind of thread, or you can use segments for a straight thread too, and then this tolerance comes into play on how long the segments are. But we're doing it with arcs here, so this doesn't so much matter. Then we're taking 5 passes in the outward direction or the radial direction, and if you look closely at these passes, you can see that they're varying in depth as it goes out. So the first pass is a little deeper, it's 55% of the thread height, and then the second pass is 30% more, and then 10% more, and 5%, and then the last pass, because we're taking 5 passes, is at this actual size of the thread. Now the only thing I could hope for here that would be nicer that Fusion does do is it'll allow you to check a box to take a spring pass. That would be nice here, although you could probably put this last pass at 0 and these others to add up to 100%, and it would effectively do the same thing, but they only allow you to get 5 passes here. So usually I do it like this. In tougher to machine materials, this seems to work pretty good. In softer materials, you probably could take the thread in only a few passes. Stock allowance is 0. Now we're offsetting the tools. We're not offsetting the tool's path by the radius of the tool in this case. This is the way I prefer to run a thread, but let me change this setting to yes, offsetting it, and you'll see the difference here. See how now it's traveling on the center line of the tool in this tool path, and this could work. You can still control the size because it's still going to have left-hand comp here, and so you could control it with the wear offset on the machine, where you'd put your tool diameter to 0, and then you would just use the wear offset to control the size, and you could go plus or minus that way, and you could do it that way. And then the third way is to use no compensation value at all. But if you did it that way, you would have to reprocess code every time you change the diameter of the tool and go back and forth between the computer and the machine until you get your thread to size. So that's the least desirable way to do it. So I usually do it like this I don't offset the tool path by the radius of the tool, and then I use left-hand comp, and then I have full control at the machine. I'll enter in the diameter of the tool at the machine, and I can adjust the size by using the wear offset. So this allows me the most control at the machine. That's the way I prefer to do it. Then here the links on this software this is the clearances above the part where it rapids, this is more like a drilling cycle in a way, because this clearance here would start drilling on a drill, but on the thread cycle it's not so much coming into play. Just this 1-inch full clearance is, which is going to rapid to before it goes down this hole. So the start and entry, the start and end, I should say, that where it goes in and out of the hole is going to be in the center of the hole here. If you were doing a big diameter thread, you would not want to do this because you'd be cutting a lot of air to get out there. And the entry method, or the lead in and outs, or arcs here. And you could do this arcs, or you could do it radially, or radially it looks like that. It just goes straight out, but this puts the most load in the tool because it's plunging right into the work when it does this. So I prefer to use this arc in and out. This other one would be more applied to an OD thread, where you're running a line that's tangent to the diameter, not so much on an ID thread. And this edge clearance has to do with, let me redo this now, and you can see it right here, how much clearance it starts the arc on the first pass mostly here, although it does it on all of them, but the first pass is the most critical really, when it goes into the lead-in arc. And I like to have this set pretty close, between 1/1000th to 10/1000th of an inch. Let me increase the size of this, and you can see what it does. See how it's out here further, but it makes a smaller arc coming in, and I feel like this smaller clearance here has a more gradual entry into the thread when it does it that way. So what did I mean about here, back in the strategy about down and up? Let's look at this on the simulation, and we'll see how it's going downward in the passes, and it's also going radially outward the same for every pass till it gets to the full diameter. If you were to reverse this and come up, it's going to start at the bottom of the hole. Let me slow this down just a little bit, and you're going to see the problem with this is it's going to wear out the top of the tool here faster in harder to machine materials, and then you have a little problems with your thread gauging, because part of the thread is there's little sections that are going to be a little bit undersized because the tool is worn more at the top, and I found that going downward tends to work better with this type of tool like that. So that's that cycle, and then this one is using a thread milling cutter. That's the full cut length. It has a 1-inch cut length, and if you remember, we're going 900,000ths deep, so it only has to take one revolution to do the thread. But you see on Esprit, if I change this to say a 1/2 inch cut length, and then I regenerate or rebuild the tool path, see how it automatically figures out how many passes in Z it's got to take. So this is something that Fusion doesn't do, and it would be really nice if they could make it do this. But other than that, this threading cycle is identical to the one on the left. It's just the tool definition is different. So I go back here and redefine the tool at the 1 inch cut length, and then rebuild the tool path. You can see now it's totally at the bottom. So let me run the simulation on both of these threads. Oh, you see that's coming from the bottom and up. See, that's not what I like. I prefer that to go downward like that. So let's run it again. Now it's starting at the top and coming down. And you're going to see this in the video, actually milling it this way. And then this is the full cut length tool, which only has to make 1 revolution to cut the thread. So that's the threading in Esprit and how it works. And next we're going to look at the threading cycle in Fusion and see what the differences are. Here we are in Fusion, the exact same model and program, as close as I could get anyway. I drew this one in Fusion and I drew the other one in Space Claim, but other than that, I tried to get these two programs to be as close as possible to being the same. So let me just quickly run through the graphics here so you can see what's happening. So there's the two drilling the holes, and this is milling the front of the part off, the same as in Esprit. And the chamfers and the threads. You can immediately see the difference in that left-hand threaded hole from Fusion and Esprit. Let me run that again and just show you the thread on the holes here, and we'll get a slower look at that. See how it goes all the way to the bottom, and then it does every circle all the way to the top. And this is really the only way you can do it with that short a cut length in Fusion. They don't have the option like in Esprit to take multiple passes at different depths. Now you could, I suppose, have a whole bunch of threading cycles and simulate the same thing, but it would be a lot more cumbersome to program it that way. It's possible you could make it to do it, I guess. That's the way that one. Now this side is almost the same. The only real difference is you see the depth of cut is very shallow after even 2 passes. And then it takes, all the passes are even depth of cut in the radial direction. So in a threading cycle, this isn't the most ideal scenario because you're taking deeper depths of cut or you could look at it like the contact area of the cutting edges is much greater when you get down in there with a threading mill compared to the first passes, which is only the tips of the thread. So that's the graphics. Let's look at the actual threading cycle on this thread here and see what the differences are here. Of course, the same thing applies as far as the tool data. Here, if we look at the data for this tool, the pitch of the thread here and the number of teeth, they call it, or points that the threading tool has controls what it does in the threading cycle, just like Esprit. The same exact thing happens here pretty much. So that's not too much different. And so these are just the feeds and speeds. We're not going to discuss that because that's really and then this here is the selection for the hole and where it's coming from in their software, and here is just the heights, the clearance, and where it starts to feed and various things like that.
which is virtually the same. It's entered differently in this software over Esprit, but it's virtually the same information. And here's the actual threading cycle part of it. Now here's the pitch of the thread, which comes over from the tool itself. The start angle, like you saw, there's an angle, you can rotate it just like in Esprit. It's a right-handed thread. The only real difference here is how you enter the diameter information. On this Fusion, you are basically subtracting the ID of the hole from the OD of the thread, and you're entering that dimension right here. This I'm not real wild about. It ends up being the same thing, I guess, in the end, you could argue, but I'd rather enter in the major diameter and the minor diameter that my part has. That just makes more sense to me. And this here entry would be if you were doing more than one start of the thread, which we're not doing here. This, again, is the compensation settings. So you could do it in computer, which is no compensation, it's just centerline toolpath. In the control, like I discussed before, is all the entries in the control that control it. And the where is if you were doing centerline toolpath, but you were going to enter offset values in the where entry on the machine. So that's virtually the same. This is multiple passes outward, which we're taking 4 passes outward like I was in Esprit, but the step over distance is even here, which, like I said, is not the most ideal scenario. This would be nicer if you could set a percentage of the total depth, which would be this half of this 78 thousandths, be on the radius, and you could set a higher percentage of cut for the first passes, because a threading tool that works better. And then this repeat pass, Esprit doesn't have this, which I wish it did, which is kind of like a spring pass. If you hover over this, it describes it, and it's just like a spring pass. And that would be nice if Esprit had that. And this is the direction of milling, which is climb cutting on the inside here, and zero stock to the lead. And also here in Esprit and Fusion, this is very similar. The lead in and outs movements. You enter them slightly different in this software, but it amounts to the same thing. You know, you can do a helix in. This are the helical leads, they call it here, and these are the dimensions for it. In Esprit, you're actually giving it the dimensions of the outside, so the radiuses. And these dimensions appear to be more of the centerline toolpath dimensions, but it comes out the same. So that's the main differences between the two softwares. In some respects, I prefer the Esprit's thread milling cycle, but of course it is a lot more expensive software.